is about adding the class and force adding the class. If there are spots and you have an adequate set of prerequisites, we can get you added to the class. If you're not sure about the prerequisite, you can message me, but here's a litmus test for you. So can you pick up a grad level inference text and read it? And understand what it says. And make sure that you can be responsible for that level of material. And so if the answer to that is yes, obviously you've gone through some set of prerequisites. Statistics is a little bit complicated because there's so many different versions and variants in different departments. But if you can cobble that material together to form the prerequisite, I'm okay with that. And so basically, if you don't understand what I'm asking in homework 0 for form the posterior and the expectation, you are in the wrong class. And so that is a fairly straightforward calculation. I'll remind you that likelihoods don't need to be normalized. And so we'll be talking about that in this lecture, but probability distributions and densities do. And so the key to homework 0 is normalizing everything. So that's it. And so, but if that's a big hang up and you don't understand the notation, you probably need a probability class or something. Okay? So again, shoot me a note if you're confused about what the prerequisites really look like. But I want you to be able to union everything together to get that graduate level inference class. You've taken some graduate level class in the calculus and the linear algebra that we're going to be using through this class. In all of our examples, isn't going to be too much for you. Okay, website here. So www.ax.stat.bt.edu/Lehman will bring you to my website. We'll re-navigate that in just a moment. I do want to make a note that homework 0 is going to be due on Wednesday, September 4th. Sorry to disappoint you. We won't be holding class on the holiday. And so I know half of you are going to have broken hearts. You can still show up. I just won't be there. So if I ever do that and I make something due on a day that we're not having class, it's always going to be the next class. Okay. So for our class, you'll be clicking on courses taught, navigate over to Bayesian Stats. Here's the basic structure. So we are going to be covering some philosophy. What is probability? Who are these players? What do they believe? And so where did the fights come from? And then what do we all agree on now and where is there still controversy? So we'll be covering a lot of that. Fisher versus Naiman versus Jeffries. There's a paper that I'm going to present to you, and it's going to ask the question, could they ever have agreed? So anytime you see one of these statisticians' names, go look them up. See what it is that they do. Their reasons for believing things have something to do with what they do for a living. And so what field they operate in. And so the question will be, can these guys ever have agreed? And the answer to that is no, never, not on anything, no matter what. And we'll be presenting some statistical questions that they disagreed on as well. We'll try to decide what is right. We will be talking about things like the likelihood principle, but I'm not going to be dwelling on it. We'll be understanding maybe what's its significance in Bayesian statistics, and then we're going to move on. So basic Bayesian constructions, how to form likelihood priors, what are the priors, which ones do we use and why. If you know how to put together a likelihood, you know which priors to choose, you understand the impact on the posterior distribution, you are a Bayesian, you are in the game. So that's ultimately what all Bayesians do. Exponential families, conjugate priors, we'll be kicking that off. We'll be talking about it a little bit today. So kind of the simplified analyses, the 1960s analyses. Asymptotics, Bayesian t-tests, so we'll be doing a lot of comparisons, but then we'll be building everything up to mixture models, hierarchical modeling, and all the things that Bayesians do really well. Then we'll get into sequential updating. We'll talk about all the different types of priors, objective priors, subjective priors, empirical priors. And so this isn't just one school of thought on Bayes, but we'll be trying to combine it all, and I'll tell you what my experience is with it and what I actually do and why I do it. And then we'll be talking a lot about the computation as well. And so all the computation that we need to know and be able to do if we can't actually do the calculus with pen and paper. And And so most complex hierarchical models, we're going to need the computation. Okay? A lot of the stuff that we do where we can do pen and paper, it's going to be to exemplify the idea, and that's where I'll be using the blackboard, but then I'm going to be switching over to my computer and showing you how to do things in a grander sense. The syllabus is here. We went through this last time, so you know where you're at, you know where my office is at. I have an open door policy. If I can help you, I will. So please be organized in your questioning. We do have some office hours, so Phil, our TA, if you could raise your hand just real quickly. So he'll be taking care of your homework. Sierra, if you could raise your hand real quickly. She'll be answering a lot of your questions and doing review sessions with me. Also, organizing the class, filming everything, and keeping us all on track. So Phil's office hours are going to be 5 p.m. on Mondays. If you have questions about the homework, that would be a good time to go and see him if you want to see him. Yes, please. We'll find out when it's due. So it'll move around, but oftentimes it will be due on a Monday or a Wednesday. And so you would want to probably use his office hours, not for how to do every single problem. I think Sierra would be a better resource for that, or me. But Phil, if you have questions about the grading on your homework, then you can go and see them. So retrospectively, that will still be useful. Make sense? We'll make sure that we have some hours for you guys when you're going through the problems and trying to get perspective answers. We'll get a location for Phil. I think he's still trying to figure out where he sits in the department. So he's an incoming student. He has strong foundations in Bayes, but he hasn't gone through this class, so some of these problems will be new to him as well. And so that's why we'll be working with Sierra on the perspective part of everything, because she has done this class. Presumably, I know how to do this stuff as well. Okay, we've got a breakdown on graded work, 40, 30, 30. So pretty balanced. Academic honesty we've covered. If you think that you're doing something unethical, you are. And so let's figure out a way around that. And so there's always an ethical pathway to solve all of your problems, I guarantee you. So it's just a matter of figuring it out. If you think that your work hasn't been graded correctly, come and see me. So don't squabble over a half point, it probably doesn't matter, but if you're so inclined, I'll have the patience. This is your main reference for the class. This linked schedule, and it will have all of the assignments. We won't be using Scholar or Blackboard, so you do have an assignment out right now. This is homework 0, and it references this paper, when did Bayesian inference become Bayesian? When did we start calling it Bayes? And so you can go there, click on that. The LaTeX file that generated that is right over here, and here's the paper that you'll be reading later on in the week. So it's an exceptional paper by Steve Feinberg. He spent the bulk of his career at Carnegie Mellon University. He passed away a few years ago, unfortunately. So his legacy still lives on, though. We can study what he said. Okay. So I think that's it with the logistics of the class. Are there any questions so far? No. Well, let's get back to this presentation that we started getting into last time. And I'll just take it from the beginning. Technical problems. Programs are crashing. I think we'll be okay. Okay. So, very brief introduction to Bayesian statistics. I'll essentially tell you everything you need to know in this presentation in just one moment. So we'll be covering a little bit of history, likelihood functions, prior, posteriors in an example, and Later on, we'll have to append all of the computation that we really need to do this in sophisticated settings. So not quite yet, but that computation explains this explosion in the usage of Bayesian statistics. So this plot is meant to show usage of Bayes or discussions of Bayes. And so I've co-located dates in historical documents with the usage of the word Bayes or Bayesian or something of the sort. And so that word has been used since the inception, but not too regularly. And so it started getting used a lot more, and this also reflects just the usage of Bayesian statistics in general. And this ramp up is because of the computation. So that's really, I think, what turned a lot of people Bayesian is. It wasn't the philosophies and all of the promises that come with Bayes, but simply the fact that you can now use it. And so that's responsible for its usage. No surprise. So our Bayesian tree, I have rooted at Laplace. If you read through this paper, you might sympathize with me and also say that Bayesian statistics is rooted at Laplace. Of course, there's a case to be made for Thomas Bayes being responsible for everything. Statistics is born in the early part of the 1900s. Carl Pearson and Fisher start going at war with each other. So let me just point out, they didn't agree with each other. They didn't like each other. And so they were rabid towards each other's views throughout history. So just because they sit on the non-Bayesian side of this trajectory doesn't mean they all agree. Fisher certainly didn't agree with what was going on over on the other side of the tree. However, you have to be careful that opinions change over time. So if you study Fisher's opinion through time, you'll see that when he's about a 60-year-old, closer to retired faculty member, he starts saying maybe what I've been doing is Bayesian all along. We also have those quotes, not all the negative ones. I think those are important. And then we have the modern Bayesians down at the bottom of the tree. And so MCMC, Gelfand and Smith got together, wrote the original Gibbs sampling paper, and I think that explains the hook in the usage of Bayes. Because once that paper came to light, people knew how to do Gibbs sampling, which I'll teach you in this class. Everybody started using this new paradigm of statistics, but this new paradigm isn't new. It's actually quite old, 1763. So the history begins with this basic formula. And if you read through Bayes' original paper, you won't see this formula expressed the way that we're writing it down here. That paper is published on the departmental website, so if you want to have a read through it, you'll notice that people speak differently and they write about mathematics quite differently. So it's a little bit of a challenge to get through that paper and understand exactly what Thomas Bayes was saying. Lucky for us is everybody's regurgitated it a million different ways and revamped it, modernized it, and come up with all the grand utilities that you're here for to study about. So Bayes' theorem says probability of A given B can be formed from the conditionals of B given A and the margin on A, the probability distribution on A. And so if I rearrange this formula like we did last time, I just have probability B given A is going to be equal to probability of A given B, probability of A divided by the probability of B. So the denominator that I've expressed as a sum, by just breaking the sum into two bits, conditioned on A and conditioned on everything other than A in that space. So that's everything in that whole space. And so what we're doing is we're forming the joint distributions of B and A complement, and then we're just marginalizing out A. Sierra, please.
You want to check your math? When I do the probability of A given B, probability
Ah,
of B,
yeah.
so, and then marginal on the B on the bottom.
Indeed.
Correct.
So I've written it differently than what we did right there, but it is the exact same formula. So if you can bear with my incompetence as a faculty member and I exchange everything, so when it's arbitrary, you'll notice that these really are the same formulas at the end of the day. And so I've just exchanged all of the notation. So what I did last time is I just wrote this down as probability of A right here, multiplying both sides. This right here is the joint probability of B and A. Is equal to the joint probability of A and B. So there's assumption about the exchangeability of both of these things. If it's going to be equal to each other, the left and the right-hand sides, what we're assuming is these events are exchangeable. In a time series, this wouldn't exactly be true. So, but if we're just talking about event spaces, then it doesn't matter if I see B and A, it's the same as seeing A and B, these two events. So what I will point out is that Thomas Bayes wasn't recognized for this contribution before he passed away. And so the beginning starts with Thomas Bayes passing away. Bayes didn't actually publish his paper before death. Instead, Richard Price found this. So the publication in question, essay by Richard Price to John Canton, FRS. He writes, "Dear sir, read December 23rd, 1763. I now send you an essay, which I have found amongst the papers of our deceased friend, Mr. Bayes, which in my opinion has great merit and well deserves to be preserved. Experimental philosophy, you will find, is merely interested in the subject of it." I will point out that people spoke quite a bit differently. This is a compliment to say that this field is merely interested. If we said that nowadays, we might think that they're not interested. But he means it in the contrary sense. And on this account, there seems to be a particular reason for thinking that communication of it to the Royal Society cannot be improper. At the end, he says that your inquiries may be rewarded with many further successes, and that you may enjoy every valuable blessing is the sincere wish of, sir, your humble servant, Richard Price. And so they do really speak differently. And so you have to get through some of this. If you guys are looking to get on my good side, addressing me with that sort of formalism would be appreciated. So, but not expected. Okay, so he sent this off in the Royal Society and decided to publish it. And so, essentially, let me show you what modern day Bayesians do with this formula. So Bayesians take that formula and they basically write it just a little bit differently down below. And so everybody uses that formula on top. That's Bayes' theorem. It's provable. It's true with densities. It's true with discrete measures. It's true with continuous measures. It's true. And so that is the relationship between conditional distributions. So ultimately, I can flip the conditioning using Bayes' theorem. This is what a Bayesian does with it. They'll write down the likelihood function, and I've written this down a whole bunch of different ways. And let me just take a moment to explain to you some notations. And I wrote it this way on purpose, although throughout the class I'll probably change my notation a little bit. And so, likelihood functions. Okay, typical notation for these. And I'll write down D is equal to data. So it's the data that you've observed, and theta are parameters. To generate data, you have to have had parameters. There has to be a distribution that you're drawing from. However, that's not what we get to observe. In inference, we're trying to learn those parameters given data that is produced out of that model. And so, typical notations for a likelihood function might look like this. Likelihood of theta given D, or data. So, or, sometimes you'll see people write it down like this. Likelihood of D, theta. Now, there are advantages to using these two different notations at different times. And this is a major point of confusion for most students that first take a Bayesian class. What I want you to appreciate before I say what these notations imply is that when people write them down, as long as they say the likelihood, they mean that it's a function of theta, and D, the data, is fixed. Okay, so a likelihood is variable parameters. It's a function of parameters, and the data has been plugged in. And I'll give you an example in a moment. So this notation that I've used on the board expresses that the likelihood, because I've called it a likelihood, is a function of theta, and I plugged in the data. So I have a likelihood model. If you have a statistical model and you have data, you can write down the likelihood. Okay? Maybe not analytically, but in spirit you can do it. And most of my class will be able to write it down on the chalkboard, what it actually looks like. But I've got a likelihood function, and it's a function of the parameters, and data is plugged in. That is all likelihoods. The reason I wrote it down in this format is we can see Bayes' rule through it. Okay, so if I take probability of B given A times probability of A, it flips the conditionals around. Okay, that's what it does. Everything in the denominator is a normalizing constant. It scales everything, so the probability space adds up between 0 and 1. So I've used this exact same notation, where I've got a likelihood function, D given theta. This is a function of theta times my probability distribution on theta, and that's a prior. And it's going to flip the conditioning around, and it's going to provide us a posterior inference on theta given the data. Now the reason I don't usually use this notation, I've used it here, and this is about the only time I'll use it here, is we can see Bayes' theorem, the analog between the thing in the top and the bottom. And so in the denominator, instead of writing a sum sign, I've written down an integration operator. And so, which is summing over continuous spaces. So I'm assuming that theta is a discrete measure when I end up writing d theta right here. So I'm integrating against the real number line. And so, but it's just adding everything up. And so the top and the bottom look about the same. The reason I don't like using this notation in general, even though I can see Bayes' theorem, is that bar usually means given. Usually means conditioning on. And so if I use this to mean given, then what it means is that theta is fixed over here. So I like my conditioning bar to always mean that the things to the right-hand side are fixed. So I usually use this notation. If we use this notation and we just plug it in, it doesn't look like Bayes' theorem anymore. It doesn't look like it's flipping the conditioning. Some people use this notation. Fx, Fd, I'll say, given theta, where this is the sampling distribution operator. And I'll be clear about this later on, but that's a little bit inconsistent because that's no longer the sampling distribution. Sampling distributions are over the data space, not over the parameter space. But you'll see people plug this in because it looks like Bayes' theorem. Okay, we need to get past that notational difficulty. What I care about is that you understand likelihoods are functions over parameters and data is plugged into it. I think that's what this notation says, but we don't see so clearly Bayes' theorem. Okay, so let me provide you an example. In a nutshell, this is all of Bayes. Write down the likelihood, multiply it by your prior. You have a posterior. Tell me about where you believe theta lives. So Bayesian analysis gives you a posterior distribution. After we've seen the data, this distribution tells us where we think the real parameters are. Okay, so it's quantifying uncertainty in those parameters. If you do this calculation, you are a Bayesian. So my old joke to this class is, class dismissed, I've just showed you what Bayes is. That's it, write down the likelihood, multiply by a prior, and you're done. Of course, if we come up with really funky prior beliefs, our posterior inferences aren't going to mean anything. And so we've got two contributions, one that comes through the data, and then one that we presuppose. And if we weight what we presuppose too much, we're not going to get good data-driven inferences. And I have to teach you in this class what are good priors, how do we choose them, what are their properties as they lend themselves through the posterior distribution. So let me show you an example. Let's imagine we're flipping a coin. I'm sure you've all seen this if you've gone through the prerequisite set. If I want to model a coin flip, what is a common distribution for modeling that? Right, a binomial with n is equal to 1, which is also called a Bernoulli distribution. And so we're going to flip a coin and we're going to try to figure out how much information is there in one coin flip, one side to that coin. I asked it a little bit facetiously how much information is contained in 12.5 cents, since we only get to see one coin flip and one side of the coin. So this is a simple example. There's a couple different ways you can address this question. Let's say I flip the coin a whole bunch of times. Maybe I want to ask the question, what is the probability of landing heads? Okay, that's what I'm referring to as P. And in classical statistics, they usually jump the gun and they'll ask the question like, is P equal to P naught? Okay, so they'll make this assumption that P is equal to P naught. They'll look at data, see if the data falls into a reasonable range of a space. If it falls into some extreme range as referenced by the null hypothesis, then maybe we want to reject that null. That's the typical Neyman-Pearsonian setup to utilizing p-values, which is different from what Fisher said. And so they might ask a question like this. A Bayesian can ask this question, but a Bayesian really is coming up with a posterior distribution conditional on the flips of the coin. So we're going to talk about both of these calculations so that we have an understanding and a comparing and contrast of different paradigms. So a Bayesian is going to try to figure out what the posterior distribution of P is. So typical Stat 101 sort of thing is do a null hypothesis test. So a Bayesian is going to say compute the posterior. So compute this posterior distribution. So how are they going to compute this posterior? You take the sampling model and you envision it as though the parameter is now unknown. So you plug in your data right here, and as soon as I plug it into the sampling model and I let the parameter be unknown, that is now called the likelihood function. And so I've used now a different notation for this altogether. Multiply by my prior distribution and I update my posterior. And so everything on the bottom is just normalization. It's the stuff that makes everything add up between 0 and 1. So likelihood function, prior. So the question is how do we form our prior distribution? So maybe you know something about the coin that I'm flipping, and you can encode that. Maybe you don't know anything and you want to encode ignorance as to what the coin I'm flipping is, and you want that ignorance to have as little impact on the posterior as possible. Okay. So you might think multiply by 1, that's as little possible impact as I can come up with, and it seems that way intuitively, and maybe that's true for some problems, but not for all problems. And it turns out there's a better prior choice. In either case, whether or not you know something about the coin that I'm flipping or you don't, you just want to know P as accurately as possible. That's the goal. That's the name of the game. So what we need to do is we need to get our posterior distribution by writing down the likelihood and then writing down the prior. So let me switch over to the board real quick and just write down what our sampling model is, what our likelihood is. Then I'll show you some simulations and show you what all this math means. So here's our setup. We'll come back around and lock down our review sessions, I think probably next time. So I erased it, but keep whatever your calendar choices are in mind, and we'll come back to it next time. So here's our setup. So xi's are going to be coming from a Bernoulli distribution with parameter p. And that measures the probability of xi being equal to 1. 1 minus p is the prob of xi being equal to 0. Okay, we could call these heads or tails if you want, but I like to work with numbers. When we take it over to a computer, eventually we have to change these into numbers anyway. So these are just called indicator functions, right here. These are indicators. They indicate what happened, whether or not the coin landed heads or tails. And so I need a sampling model for this. So I want to write down fx I given p. This is our sampling model. So I need a mathematical description of what I've just written down using a lot of words. So how do I write down this distribution? If you'd like, I could write this as probability of xi. This is probably the biggest curse all through statistics, is that leading letter. What we use for all of our distributions, densities. So a lot of times we recycle it. It shouldn't necessarily be recycled. Just have to understand what it represents. So this is the probability of xi given the true probability p. So what is this? How do I write it down?
So we can take a Bernoulli distribution and plug in p to that parameter.
I can, right. So I can also plug in n is equal to 1 into all of that. Right? Because it's a binomial distribution. So how do I do it? Why don't you come up and show us? You got it. This is a Stat 101 question. What's your name? David. All right. David's going to show us how to do it.
The Bernoulli distribution expression.
Give it a shot.
It's there.
It's there. It is.
I can maybe explain that.
Okay. Let me explain. And so I would write it down like this. Here, have a seat. No. And so what I could do is I could use that expression right there, or I could use something else. Let me just go straight to the Bernoulli, because I've said this is just a distribution over one of the xi's and not the sum of all of them. And so what I've written down is the binomial distribution is the distribution of the sum of all of the xi's. A little bit different. But this is going to look like this. P raised to the xi, 1 minus p raised to the 1 minus xi. So I have these things right here acting as switches on the model. If I plug in xi is equal to 1, this is a 0. Something to the 0 is 1. This is a 1, so this is just p. If I plug in a 0, this is 1 minus p. And that's exactly what I wrote down right over here. And so I've encoded it mathematically, so it's either p or 1 minus p, depending on if I plug in a 1 or a 0 into that. So that's the Bernoulli distribution. What's the sampling distribution for all of the xi's? So slightly different question. Get my demo up and running while you think about that. So here's this, my question. What is this is the joint distribution of xi's. So I flip it n times. I flip the coin, I see n realizations of the coin flip.
You have
If they are independent, it's the product of all the individual.
Perfect. So if they're independent, I haven't said exactly if all these xi's are independent. So usually we'll do something like this. Say this goes from I from 1 to n. And then we'll say something like xi is independent of xj for all xi's given p. That's what Christina is saying. They're conditionally independent. And that's the way we use this language. They're independent. But keep in mind, the xi's are not independent. Data is never independent of each other. They're conditionally independent. Given knowledge of the parameters, then they might be factorized. You cannot factorize all these xi's out of the sampling model if you don't know what p is. But given p, you can come up with factorization. We'll be discussing that in more detail. But thank you, Christina, for reminding us. These are conditionally independent. So given p, all the xi's factorized. Bless you. So what is this? This is going to be the product. I goes from 1 to n, fxi, given p. So this is going to look like p to the sum of the xi's. I goes from 1 to n times 1 minus p to the n minus sum of the xi's. I goes from 1 to n. So that's our joint distribution. What I had written on the board that Naveed pointed out to us, and he could explain it, was a slightly different formula. Binomial representation is a little bit different. So if we were to model some of the xi's, this thing right here has a binomial distribution with parameter p, then we would have f sum of the xi's. I goes from 1 to n, given p. This is going to be n choose sum of the xi's, p to the sum of the xi's. I goes from 1 to n. 1 minus p, n minus sum of the xi's. That's the binomial sampling formula. They are different. And so, saying that, I could use either one for this problem. So let me make that statement. Doesn't matter which one I actually use. If I plug this thing in, or if I use this. I'm going to ask you the question, why doesn't it matter? Had an inference class, you'll know the answer to this. Or learning, P. We might call that inferring or guessing, but I like to say learning. It makes it seem like we've done something. We could either use either fx, I'll say this, product I goes from 1 to n fxi given p, or I can look at f sum of the xi's given p. So these are Bernoulli's. And this one is binomial. Why does it not matter? Which we use. So this doesn't depend on the data. Kind of does, right? So it matters how many successes. It does depend on the parameter, right? If I switch the parameter and I made p really, really high, that sum would become really, really big. If I made p very small, we wouldn't see many successes. So when I added up all the xi's, that sum would be small. So it certainly depends on the parameter. And it depends on the parameter in such a way that I don't lose any information about the parameter. And so what I'm saying here is that it doesn't matter if I know all the xi's or if I know the sum of the xi's. Keep in mind, this thing is one-dimensional. It's the sum of a bunch of ones and zeros. And all of the xi's is n-dimensional. So what I'm actually saying is that the sum of the xi's contain all the information about the parameter. Don't lose it.
Sufficient statistic.
It's a sufficient statistic.
So essentially, these two are off by a constant factor given the data.
That's right. Absolutely. And that's in terms of the density or the measure. They're off by a constant factor. And so in inference class, we would learn sum of the xi's is sufficient. It has all the info. About P. What's your name in the back? Ben. Ben just told us that we're off by a constant factor somewhere. I want you to look at this model right here and look at this one. The constant factor Ben is talking about is this thing right here. And so it turns out that if the conditional distribution of xi's given the sum of the xi's is a constant, then the sum of the xi's is going to be sufficient, or whatever that statistic is. So if I have a statistic, it can go either way. A statistic given all of the other data, or all of the joint data given that statistic, whatever that conditioning is that thing is not a function of the parameters. What that means is that I can take this model, and I can divide it by this model right here, and there's no more p's in there. This part is the only part that depends on P, and it will cancel that out. So that's the technically rigorous thing. If you want an understanding of that, take my 5114 class and I'll march you through that. And so what all these technical definitions are. Some of the xi's is sufficient, and so I could just model some of the xi's. Here's one way you can figure it out. This is the factorization theorem in disguise that you would learn in 5114. I wrote this down, and I was able to reduce all of the xi's. So instead of writing out all of these into this product and expanding it, where all of those xi's are either a 0 or 1, I've been able to compress it into this sum. And I can't compress it any more than that. And so that maximal compression says that this is minimal sufficient. So I didn't even use that. I just found out all I need is this formula right here. Here's another reason it doesn't matter. If I plotted these shapes right here, so if I plotted this equation as a function of P, it would look just like this. Same exact shape. This one would be scaled up or down. Okay, so this is going to be some big number, so it's going to be scaled up. So they have the exact same information, meaning that if I take the ratio of those two shapes, the shape gets knocked out of it. That's what it means to be sufficient. Okay, so that's one part of our Bayesian model. So what we're going to do is, here's the joint sampling distribution. I really don't care about that, but we'll talk about the analysis if I did use this model. Let's get rid of it right now. Go back to this one. So I've got my sampling model. Is going to be P, sum of the xi's, 1 minus P, n minus sum of the xi's. I'll drop the index in. And so this is a sampling model if P is fixed. So where P is fixed and xi's are random. What that means is the xi's are variable. It's a function of the xi's, but I get additional properties when I say that it's random. It has to adhere to a probability measure space. We'll talk about that later. So, however, we could also write down the likelihood function. The likelihood looks like this. It's going to look like this. P to the sum of the xi's, 1 minus P, the n minus sum of the xi's. Looks exactly the same, right? They look equivalent to each other.
Let's fix the place.
That's the caveat. Where xi's are fixed and P is variable. And so it's a function of P. It's not yet a random measure. I haven't done any probability calculations on this. It's not yet considered a random measure. I haven't dropped it into a probability space. I have to do something to it first. But they look like the same expressions. Usually I'll write this down as LP given some of the xi's. And I'm going to write this down as proportional to that. So this is proportionality. Meaning that I can multiply by any positive number, and it's still the same likelihood. All it's going to do is move it up and down. It's not going to change its shape. So if you can't envision this shape what it is, I'll show you soon. Show you at the beginning of next class. We'll simulate all of this and understand what's going on. And so here's the likelihood function. So here's the key to getting the likelihood function. Write down the joint sampling model, plug in all of your data, and then discuss all of your parameters as unknowns. They're totally different functions. Let me show you real quickly. Here's an example, and then we'll close out. We'll need to talk about the prior, but we're halfway through Bayes. Because we've got a likelihood function, and I would say that's the driving force of inference. If all of your inference is coming through the prior and not through your data, don't be surprised if you're wrong. I like starting with the binomial example versus the normal example, because when I draw these functions, for a normal example, they look almost exactly the same except for the labeling. But for a binomial example, a likelihood and the sampling distribution look entirely differently. So this is the sampling distribution for a binomial. If I plugged in P to be 0.7, and n was equal to 10, this would be the distribution. So binomial is measuring the number of successes we expect to see when I flip the coin 10 times. So this is its distribution. It can't be greater than 10. I can't have any more than 10 successes and 10 flips. And so P is fixed in this, and then I can draw the distribution. If I don't tell you what P is, it's not a distribution yet. It's a family of distributions. Here's what the likelihood function looks like. Looks like that. It's continuous. This is a measure between 0 and 1, not between 0 and 10. And so as functions, they look entirely different. So the sampling distribution and the likelihood look the same when I write them on the chalkboard. But when I actually wield them and I use them, they're totally different things. So again, likelihoods, where you take your sampling distribution and you plug in the data, and then you free up the parameters. To sample data, you need to know what those parameters are. So what we conceptualize is that there's some sampling distribution out there controlling the randomness over our observations, and there's some parameters guiding that distribution. We get to see data, and we want to learn the parameters. And so one kind of philosophical question is I know the relationship between P and the data in the sampling distribution, so why shouldn't I just use that exact same relationship when I infer the parameters? It makes sense that you should use that relationship. That's what the likelihood is binding you to do. So for the last part of our analysis, we need to take this likelihood, we need to multiply it by a prior, and then see how well it performs. That's what we'll do next time. If you would like to get ahead, look up the word conjugate prior. That's where we're going next. Thanks, you guys. That's it for now. I'll be around for a couple minutes for me to talk about anything.